Welcome to the Fort Worth Astronomical Society, June 16th, 2026. And this is our general meeting we hold once a month. Next slide. Help. I think it's, do we have any guests? Hey, tell us how you heard. Do we have any visitors? Nice. Okay, tell us how you heard. Share your journey and what equipment do you have?
I heard it from her. I heard it from her, so pass over.
And I had heard about it from the Corpus Christi Astronomical Society, because I used to be from there and then moved here. But I don't have any equipment, so.
Can we fix that?
Yeah, we can fix that.
We have a lot of equipment that y'all can use and a lot of experience in this club that will help you use it and get you started. Next slide, please. Any other visitors? I'm sorry. Got one way in the back. Can you yell or you want this? Okay.
Found y'all on Facebook. Kind of got into it via scouting. And I use a lot of the, getting into the smart scope stuff with like the CW and lab, and I'm working on a
Need the mic for YouTube. Zoom for Zoom.
Good. Okay. I just got a what?
They use that goes on Zoom.
Oh, okay. Yeah. We have Zoom visitors, and without the mic, the Zoom people don't hear it. So we'll let you go through that again.
Okay.
So I found out about y'all via Facebook. I got into astronomy with scouting, and that's where I learned all my stuff. And I use a lot of the smart scopes, primarily the ZWO series and the Dwarf Lab series. And I'm currently in the process of building a astronomy rig.
Thank you. All right. Where? Oh, well, why didn't you wait till I got up to the front so I could walk back again?
I'm not that mean. Dave Haggerty, I just joined, I don't know, a month ago. First meeting. Just moved here from Las Vegas. I like the weather there better. Skies are better.
Have you been here first summer yet?
No.
Summer's not here yet.
Yeah, I know. I've been doing astronomy off and on for 25 years. I have an 8-inch Celestron, a C-Star S50 and S30. Been a solar system ambassador for about 3 years. Volunteered at Grand Canyon for the last 2 springs, 3 months at a time. Doing astronomy at night, solar during the day, and trying to find time to sleep. Anyway, thank you.
Yeah, while I'm walking back up, I lived 15 years in Reno and I visited Las Vegas a lot of times. The biggest difference in the weather in the summer, Vegas is very dry. Here, midsummer, it's 100 degrees, you walk outside and you're soaking wet. So, big difference. Find my spot. Okay, next slide, please. All right, please welcome any new members. We have new members that are visiting. Well, one said he just joined, so we already covered that. These are the new members that we've got. Sally's? Yeah, Sally joined. Okay. Welcome. Yay. So, one thing about me is I am horrible with last names. So instead of butchering them, here they are right here. I got a funny story, but we're not going to take that time. Go ahead. Next slide, please. Okay. We were founded in 1949. We've been around a little while. Like I said before, there's a lot of experience in our club. With 412 individual members, 251 member accounts. So remember, we have family and we have single as far as the membership goes. A wide range of experience. You're into solar. You want to build your own scope we have the people here that can help you do that. Nah, I want to buy it and shoot, and I'm a photographer. I like it simple. A lot of people help. The best things as a new person or new member you can do is find out when our star parties are. Go attend the star party, even if you don't have scopes. Walk around, talk to the members. You'll learn a lot just by watching others set up and talk about the sky. And it's kind of a great experience when you're getting started and you don't even know where you want to start to begin with. So star parties are extremely information. Nonprofit organization, that's one of the things the star parties are, is our outreach program. We're really big on that. The other thing, I gave a presentation a few years ago. To me, YouTube is my friend, but you have to be able to weed out all the flakes and find the people that really know what they're talking about. We even have some of our high-end people in the club that still watch some of the presenters on YouTube because they really, some of them know what they're talking about. Let's go ahead. Okay, our mission is to promote astronomy via public outreach. You're going to hear that a lot. To encourage and support group interest in astronomy. We have several things that we do with large groups that we'll cover. The cultivate, observing, and research among members. So, don't leave here, go home, and don't watch email. Any interaction with members. Try to get involved, especially in the club. To promote building of astronomy instruments, covered that one, and make club equipment available to members. Next slide. Our resources, a member handbook, Thompson Observatory, Rising Star Observing Area. That's our big 4-acre area where you can go to out Rising Star, set up. It's a dark site. I think it's level 2. We haven't crossed 1 yet, have we? No. It's a Bortle 2. It's very dark out there. Milky Way shines nice and bright when you go out there. Club telescopes and eyepieces. And our club site online is a good resource also. If nothing else, our club site will show you other sites to go to with a higher level of information. Next slide, please. This is our rising star. If you're new, find a member to take you there first. The funny thing, when I found it, I'm kind of an adventurous one. I use the GPS on my car. It leaves you about a half to 3/4 mile short of where the field really is. So the good thing is it leaves you on a road where you've got no other direction to go. So you just keep going. 2 observatories we have, the Noble and McCatherine. If you get a permit, we now have in place a policy where you have to file for a permit to bring your RV out. We have RV parking area there. Some of the other things, no generators after dark until sunrise. This is incredibly dark and quiet and peaceful, so we don't want to mess that up. This whole field, like I said, this is 4 acres. This whole field is where you can set up your telescope. There are some pads, if they aren't already taken, you can also use, except the ones with A are possibly leased. The leases may be up, or someone may have a lease on them. I have found if they're leased, and you know the person that's leasing, give them a call if they're not going to be out there. They'll let you use it. It's not like, oh, we got a red flag on this and nobody can have it. This right here is our green building. It's a compost restroom. So we're pretty well covered on that. The astronomy building holds our equipment. There's also 2 bunk rooms in there where you can lay a cot, sleep, freeze, and burn up in the summer. It's not climate controlled yet, but we're getting there. Next slide, please. Okay, this is some of the telescopes that we have. So when I say we've got some equipment that we can loan y'all, then this pretty well covers what we've got. Most of it's out at Rising Star. So if you get with a member, go out there, we'll drag one of those out, and you can use it. We even loan them out, ones that are encased and secure to where they won't be damaged in transport. But we've got a few pieces, and we're working on still evaluating some more and getting those up and running. Next slide, please. Okay, these are our online. And when I first started this club, one of the things I found very helpful is cell phones, cameras. I was taking a lot of these slides, but this whole presentation is online also. So you can get this and cover all those areas, but a lot of information, a lot of research stuff. Let's go, next slide. Additional club members, additional info is also available at these two sites. Night Star is one of our, you'll hear that a lot. Go to Night Star, go to Night Star. They're the national end of our club here local. So we flip back and forth a lot to that one. This one's a lot of really high-end stuff that you can look at. Next slide. Okay, as of my last information, this is the ballots for the election. What I've been given and what's up on screen. It's not something I put together, but has been put together. Sai, you want to cover some of this stuff? No, you're good. No, thought you were going to. Thought you were going. No help here, huh? I'm stranded all by myself. Okay, fine. I'll take that. 2026 elect. This is the candidates for the open election position. Now, my thought was that we cover the speaker so he doesn't have to sit through all this. So, yeah. So we're gonna let Bill handle this. This is your gig, and we're gonna let our special speaker speak, and he can sit and finish with the meeting, or he can leave at his.
No, he's not leaving. I'm buying the beer tonight. So, Dr. Ashkan Salamat is from the University of Las Vegas in Nevada, and he studies extreme pressures and planetary cores. I'm just going to let him tell us the rest. Thank you.
Thank you. Yeah, let me.
You mean to set you up here?
This should be working. Yep.
Oh, you're hooked up.
Good. Thank you for that incredible introduction. Okay, so very impressive. Thank you, everyone. My name is Ash. I'm a professor, associate professor at the University of Nevada, Las Vegas, and I'm the director of the Nevada Extreme Condition Laboratory. So my confession is that I am not an astronomer. I'm an experimental physicist. I'm a condensed matter physicist. I care about the interaction of atoms at the atomistic scale. Come on in. No, you're good. You're good. You're good. You're good. Perfect timing. Actually, I'm going to have to take my glasses off because they're trifocal and I'm walking around. So, yeah, it's crazy. So, what I'm going to demonstrate today is how, from the laboratory measurements that we do, we can correlate this to the understanding of the solar system and of the exoplanets and the stars that we see in the observable universe. As I said, prior to starting my job at UNLV, I hadn't really thought about the stars. I've never really looked up. I was too focused looking down at my lasers, at my diamonds, and I'm going to explain all this to you as the story progresses. And when I came to UNLV, I met a bunch of astronomers. In fact, I was fortunate enough to meet a bunch of folks that worked on the Kepler project. And what we realized is a lot of the work that we did in the laboratory could allow us to make corrections to the data collected during the Kepler mission. So don't be misled about the title. I'm not going to talk much about the Earth, actually. I just put this title up to get you all excited about something that you might relate to. I'm going to be mostly talking about Jupiter, Neptune, and super-Earths, things that we've observed using the Kepler mission, planets that are terrestrial in their composition, and most likely 5 to 10 times Earth masses. So slide. Louder. Okay. Pardon me? Sure. Can't see without my glasses. How's that for the volume? Louder? Even, should I just talk very loud then? Okay, but I'm going to steal that bottle of water then. Is that okay? Because, yeah, thank you. Okay. So, our story really starts of human imagination. What I'm going to be talking about is places we cannot reach. We can only see marginally, and based on fundamental science, a little bit of hand-wavy gestures and understanding, we try to extrapolate into a deeper understanding of our environment. So we've often thought about what might be in the center of the Earth. Well, we know very much what can be in there. We know the composition, we know the density, we know a whole bunch of other stuff. Slide. But our journey really starts with standing on the shoulder of giants. Inge Lohmann, a Danish seismologist at the turn of the 20th century, realized that activity, seismic activity, earthquakes occurring in New Zealand were being deflected. The waves that were being generated by these earthquakes were being deflected. And this deflection most likely meant that the core of the Earth was solid. Okay, now I'm going to talk a little bit quieter. Still at the same volume. Her work revealed that the Earth has a solid core and a liquid outer core. This was a remarkable revelation at the time. Truly a pioneer of modern science. Slide. When we look at the Earth, we try to understand her composition, her density, the pressure and temperature in which it exists in. Slide. The Earth has about a radius of about 4,000 miles. And since I come from Vegas, slide, we're going to do an exercise where we measure everything in stratospheres. How many stratospheres do we need to get to the center of the Earth? Slide. So it's about 4.5 stratospheres to make about a mile. Slide. Which means you need about 18,000 stratospheres to get to the center of the Earth. Slide. Remarkably, even though we can split the atom as a species, we can go to the moon, we can see observations of billions of light years away, the deepest hole we've ever dug is about 36 stratospheres. It's in Russia. We haven't really dug any deeper. So we've dug about 8 miles. For all the great things we've done as a species, we've only really dug about 8 miles. And the reason for that is, as we dig deeper, things get harder, things get hotter. The cost to dig deeper isn't very beneficial to us as a species. So we need to make about 18,000 stratospheres to get to the center, and we've dug about 36. So there's a huge gap between how deep we can deep and how we can explore the internal findings or the internal mechanisms of a planet like ours, the Earth. Slide. One more. So how do we know what's in there? Well, at UNLV, I hang out with geologists. They're mostly hippies, so that's why I hang out with them. They're really into drinking. They're mostly out in Death Valley, Grand Canyon. We know from geological findings what could be in the Earth. We can find minerals, turn over parts of the Earth, and so on. Slide. Volcanologists. The Earth, deep in her interior, makes materials that we cannot make here on the surface of the Earth. And volcanoes allow material to be spewed out from these activities. Slide. And then there's people like me. I'm a high temperature, high pressure experimentalist. And I'm going to be talking about what I do in the laboratory with my students. We use lasers, diamonds, to replicate the interior of planets. And we do it with high precision, and we care about how atoms interact with each other. And from understanding how these atoms interact with each other, I'm going to hypothesize the interior of planets and so on. And one more slide, please. And for those of you that are interested in fusion, this is a photo of inside the reactor of the National Ignition Facility in Lawrence Livermore National Lab. They're using petawatt lasers, so lasers the size of 4 football fields, to fire on a sample the size of the width of a human hair to go to 100 million degrees Celsius to replicate the interior of a star. So there's tools available to us as humans. We try to explore our environment, we try to use laboratory techniques and go beyond the stars with the most modern state-of-the-art techniques to replicate the interior of what we think could be terrestrial, ice giants, gas giants, and solar star systems. Slide. Okay, so the Earth. We know based on gravity mass relations and hydrostatic pressure considerations, the center of the Earth is about 3.5 million atmosphere and about 6,000 degrees Celsius. Neptune, the larger of the ice giants, has a pressure of about 8 million atmospheres in her center and a temperature of about 5,000 degrees Celsius. And there's Jupiter, the colossal entity that exists in our solar system, an internal pressure of 77 million atmosphere and about an internal temperature of 16,000 degrees Celsius. Now, these are three very different species that exist in our solar system. We have the Earth, which is terrestrial rock. We have the supposed ice giants. Now, these are not ice giants. We'll explore later that they consist of water, ammonia, and methane, but most likely these are slurries of metallic fluids that give rise to Neptune's peculiar quadrupolar magnetic field. And then we have the supposed gas giants. These are not gas giants. I'm going to demonstrate with the work I've done in the lab that Jupiter is a giant ball of liquid metallic hydrogen. There's only a very small amount of gas in Jupiter. It's just on the surface. The second you start to go deeper, the pressure and temperature interact with each other, and the hydrogen that makes up Jupiter starts to exist in a metallic liquid state. In fact, Jupiter is a giant ball of liquid metallic hydrogen, and that's what the journey starts with today. So who are we? Who am I? I run a center. We specialize in hardcore experimental physics. We have some theorists that help assist us. This is our laboratory at the University of Nevada, Las Vegas. I'm a spectroscopist. We fire lasers at things. We fire 1 billion photons. Of the 1 billion photons we fire, we get one back that's a different color. That difference in color tells us something intrinsic about the properties of materials. All materials are breathing in a quantized dance with their nearest neighbors. And by using lasers and spectroscopy, we can understand what this quantized dance is trying to tell us. This photo down here, I just threw it in because it looks pretty cool. This is the European X-ray free electron laser facility in Hamburg in Germany. We use light 1 billion times brighter than the sun to look at atoms and the intrinsic properties that they exist at these extreme conditions that I'm interested in. Okay, it didn't come out so good. So, believe it or not, I can replicate these conditions of planets in my lab. I can go to about 10 million atmosphere in my laboratory. So 10 million atmosphere is about 140 million PSI. The tire pressure that you have in your car when your car tire explodes is about 35 to 45 PSI. So we're going to hundreds of millions of PSI in the laboratory. And the way we do it is we utilize diamonds. Diamonds are Mother Nature's hardest known material. They're incredibly hard, and we can squeeze materials between these diamonds. And because diamond is optically transparent, for those who have rings, you can see through the diamond. It has a high refractive index, but it's clear. And because it's optically transparent, we can fire different types of lasers, X-rays, and so on. And so we have an optical portal into the center of our sample chamber, which is sandwiched between these two diamonds. Using just this simple primitive handheld device, there's a piston, a cylinder, they come together, you tighten some screws, they provide maybe a couple of hundred newtons of force. We can get to about 10 million atmosphere of pressure inside of these sample chambers. As a condensed matter physicist, I was often interested in the fundamental properties of materials, but having met astronomers and exoplanet specialists, I realized that much of what we do can be related to help those folks understand of what they're observing. Slide, please. Okay, so I know you're all astronomers or amateur astronomers, so we're gonna do some physics today. I'm gonna hold everyone's hand. We're gonna journey through the realm of high density physics. And we're going to appreciate why what I do is so important. So the x-axis is pressure. So as we traverse along the x-axis, the pressure is increasing. And on my y-axis, my vertical axis, it's a parameter called free energy. It's just the energy of the system. What it really means is if I take any material and squeeze it, increase the pressure that the material is feeling, I walk this line. And as I walk this line, the free energy of my system increases. Mother Nature's primary goal is to reduce the free energy of a system. That's all she is ever trying to do. So as a complex mammal, that has the ability to manipulate nature, I come along, I build a diamond amble device, I squeeze my sample between two diamonds, and I increase the pressure that this sample feels, and I increase the free energy of my system. Next slide, please. Something critical happens at some transitional pressure. It doesn't matter what the value of this pressure is, it's unique to every material. Next slide. And one of two things can happen. I can continue taking the path that I was already taking, or Mother Nature can say, hey, there is an alternative path that has a lower gradient, a lower free energy pathway that you can walk. So nature often allows you to rearrange atoms, rearrange certain things to lower the free energy path you're going through. A great example is diamond. Carbon is an element. Charcoal is amorphous carbon. It's a disordered system. Graphite is a layered form of carbon, sp2 hybridized carbon. A buckyball is a fluorine atom or a fluorine molecule of C60. If you take any of these things and heat them, you can never make diamond. Carbon sublimates, it turns into a gas. To make diamond, you have to take carbon and squeeze it. It's metastable, you have to squeeze it above a certain pressure, you have to follow this path. If you just take carbon and heat it, it just vaporizes. Remarkably, you have to squeeze it and heat it, and it follows this transition to a higher density form. Next slide, please. And what's fascinating about this landscape of density that we're walking across is, once I'm in this high density form, two things can happen when I release the pressure. I can release the pressure and go back into my initial state, or just like in diamond, I can traverse this dashed line here. Diamond can be captured. How diamond is formed is inside the Earth, in the interior of the Earth. The way we can access diamonds is through volcanoes. Volcanoes spew out diamonds. Without volcanoes, we would never really be able to access diamonds. Okay, we can dig mines and stuff, but the likelihood is the biggest diamonds that we see on the Earth are a consequence of volcanoes spitting out the interior of the Earth. Because you need pressure and temperature to make something like diamond. Next slide. Just to throw another spanner into the works, my interest lies here, where things are crazy. They don't follow these paths. Nature is complex. We like to hang out in this regime called the metastable regime, materials that Mother Nature herself cannot make. Actually, that's my expertise. I make materials that nature cannot make, and I do it in a way by traversing this energy landscape in a way that nature cannot. Okay, so let's go back to planets. Jupiter. Jupiter has about the same composition of the star as our star. It's predominantly hydrogen and helium. In the case of Jupiter, the gas giant is 75% hydrogen and 25% helium. But Jupiter is not a gas giant, and I will demonstrate this through some of our observations. So, I'm just going to look at hydrogen. Hydrogen is element number one, the most simple system that we have. It has one proton, one electron. Remarkably, it is incredibly complex. We know as little about hydrogen as we do about anything else. It is a quantum state. It has all this weird and wonderful behavior that's just so hard to understand. I'm going to set up a new graph here for us. At the bottom, I have pressure. My units are gigapascals. 1 gigapascal is 10,000 atmosphere. These are very, very high pressures that I'm going to be talking about. And on my vertical axis here is temperature in Kelvin. So about 273 Kelvin is room temperature. So 0 degrees Celsius, pardon me. And so with hydrogen, you expect the following. You have solid hydrogen at low temperature. You heat it up, it becomes liquid. But remarkably, the predictions are if you squeeze hydrogen to very, very high pressures, it becomes a metallic solid. You can have solid metallic hydrogen at extreme pressures. If you go to the pressures of Jupiter, hydrogen metallizes into a solid. You push the atoms so close together that they start sharing electrons and they form a perfectly covalent bond. And a perfectly covalent system is a metal. That sea of free electrons that they talk about when they talk about metals, that's just a perfectly covalent system. And so you would expect a solid liquid interface and crazily some very, very high pressure behavior where it metallizes. Next slide. Unfortunately, hydrogen doesn't do that. The first thing I want to point out is hydrogen has a negative melting line. It has a turning point in its melting line. It is an incredibly complex system. You have solid hydrogen with multiple different structures called phases. You have liquid hydrogen. Maybe you have solid metallic hydrogen. But in 1999, Lawrence Livermore made a measurement. They used a shotgun, a two-stage shotgun, and they measured the resistivity of hydrogen. And what they found is that elevated temperatures and pressures, hydrogen behaved like a metal. Next slide. What that infers to us is that once you go past this liquid hydrogen state and this solid hydrogen state, what you enter is a monatomic metallic liquid state, most likely describing the supposed gas giants. When we say gas giants, what we're going to find out is they're not very much gas-like. The likelihood is that anything that is hydrogen-rich is going to be and as a planet will have a composition and interior pressure and temperature that exists in this realm of this phase diagram here. Next slide. Just some physics for everyone. I've been told a bunch of you are engineers, former physicists, amateurs, so much. So let's talk about some fundamentals here. I'm going to ask you a question. What is a metal? It's a very hard question to answer. It's shiny, maybe. It's reflective. According to this definition, it has an electroconductivity that goes to a finite limit at the limit of t equals 0. Bit of a mouthful. But what is a metal? It's actually a question that we actually struggle with as physicists. The thing is, this definition by Sir Neville Mott, great British scientist of the time of the 19th century, doesn't hold true. What this says is that when you cool something down, if it's a metal, it will have a real conductivity value that you can measure. If it's a semiconductor, the resistivity goes to infinity, just like an insulator. There's no electrons to sit in the conduction band. But this doesn't really work. If you take silicon, which is a semiconductor with a 1.1 eV band gap, all your cameras are silicon detectors. All the cameras that you folks use are silicon wafers laid in such a way to make a charge-coupled device. They have an electronic band structure of 1.1 eV in their band gap. These are not metals. These are semiconductors by definition. If you melt silicon, it becomes a metal. So how does this definition work? It doesn't. This definition says to you, you have to go to 0 Kelvin to be able to measure its resistance. But if you cool down molten silicon, it just turns back into a semiconductor. So what is a metal? These are very, very hard questions to answer. I'm going to skip this one. What do? We're going to set up a scenario that we think is starting to protrude into about 1/8 of the skin depth of Jupiter. This experiment is in a diamond anvil cell. It has hydrogen in it. We're at 1.7 million atmospheres in our diamond anvil cell. And we want to know how it behaves when we heat it. The problem is you can't just heat hydrogen. The reason the hydrogen economy hasn't worked for our cars is because hydrogen is highly embrittling. It destroys everything it touches. And hot hydrogen diffuses through diamond, it diffuses through metals. You can't just heat it. So we did something quite novel here. We heated it for a very, very short amount of time. This is in microseconds. This full-width half maximum, my pulse, is 200 nanoseconds. What we did is send a pulse of laser light in, and this pulse lasted for 200 nanoseconds, 10 to the minus 9 seconds. So we heated it very, very quickly. And the reason we did that is because diffusion is very slow. Hydrogen diffuses very well, but it does it slowly. So if we can heat it and cool it down very quickly, it doesn't diffuse, and we don't destroy our sample at these extreme pressures. So we send a pulse of laser light in, and we heat the hydrogen. And we measure two things. We measure reflectivity, and we measure transmission. So there's no pulse, no pulse, no pulse, and we heat it, and the reflectivity of the hydrogen shoots up. All of a sudden, this transparent hydrogen, very much like glass, when it's heated at this pressure, becomes reflective. Next slide. Simultaneously, while it's becoming reflective, we measure the transmission. So as it becomes reflective in the blue, the transmission drops. This clear piece of hydrogen, when you heat it at 1.7 million atmosphere, during the pulse of the heating, becomes very reflective and opaque, very much like a metal. We do some clever mathematical calculations. We compare it to the Drude model. And what we find is that there is a true boundary. So our work is in the black triangles. Everything else before us is theory, and we never trust a theorist. Using these experiments, we can track a clear boundary between a molecular insulating liquid, so very much something that looks like glass, and when you cross this transition boundary here, you get an opaque reflective metal. This boundary defines this insulated to metallic transition in the liquid state for hydrogen. And what does that tell us? Well, that tells us that if we start to consider Jupiter, which is a hydrogen-rich system, and in fact, since things like Jupiter, the gas giants, make up most of the observable universe outside of solar systems, outside of stars, that metallic fluids are probably the most abundant state of planetary matter, not only in our solar system, but probably in the observable universe. So when we look out, we see stars. These are just hydrogen systems that are fusion reactors. Anything else is most likely a gas giant. And when we mean gas giant from now on, what we're really talking about is giant balls of metallic fluids, most likely hydrogen with some helium in it. So we're going to go on. So I don't know how I'm doing. So lasers, pew, 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 hydrogen, bah, 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 bah. We turn something that's transparent like glass into a metal. If that was my lecture, I would answer that phone for them. We're going to move on to the ice giants. Now, once again, these are not ice giants. In fact, Neptune, the supposed ice giant, exists of, its composition is water, ammonia, methane, light hydrocarbon systems that exist in the molecular state. But actually, when you penetrate into the depth of Neptune, what you observe is metallic-like behavior. Water, methane, ammonia start to mix. They start to do weird and wonderful things. And the likelihood is that just like the gas giants, the ice giants are giant balls of metallic-like fluids. And it's why Neptune has a quadrupolar magnetic field. The Earth has a dipolar field. We have the north and south poles. Neptune has a quadrupolar field. And the likelihood of that is because you have localized dynamic behavior in these metallic fluid oceans. So what can we do about this? How can I contribute to this problem? Lots of people have been working on it. I'm excited to help out. I've got a whole team of folks that are going to do all the work for me. What can we do? Well, we tried to look at water, ammonia, methane. It is just too complicated to look at as a ternary system. We're simple physicists. We like simple systems, high precision. We want to know what's going on. So out of the three systems, we selected water to look at. The thing about water, it is even more complex than hydrogen. It's partially quantum-like. It's light. It has very weak bonding in its hydrogen bonding. There are now, this is wrong, there are now 19 known phases of solid water. Water is a very intricate, delicate system to look at. The snowflakes that crystallize on here on Earth have hexagonal symmetry. But as you compress water, the symmetry changes. And that's where I come in. I want to understand what is water behaving like when we start to look at super Earths and water-rich super Earth-like systems. We're going to skip that. Next slide. So we're back to our pressure, temperature plot here for water. Most of the water that exists on Earth is hexagonal-like on the surface. We're gonna label these using numerical values here. 7. Probably inside the deep Earth, there's phase 10, whatever this might mean to you. There's the fluid phase, and so on and so on. But what I'm interested in is making metallic water. There are predictions that water at extreme pressures and temperatures doesn't decompose. You don't get its constitutional elements. Actually, you retain the covalency of hydrogen and oxygen, but actually what happens is the electronic band structure crushes itself down just like hydrogen, and in theory, when you get to the most extreme conditions, you can have metallic water. Now, it's not something you can hold in a jar. It's going to exist in my little diamond anvil cell crushed between diamonds with a laser, and but my aim is to get there. That, I'm going to come back in a year or two and give you my talk on metallic water. Right now, I'm going to show you our remarkable data on what we've observed recently, the behavior of water inside of super Earths. So the work I did on hydrogen, I did it at Harvard. We did the laboratory techniques. It was all in-house. We spent years and years building these optical systems to try and do the measurements. For water, we've gone somewhere very, very different to try and measure its properties. We've gone to the advanced photon source. I'm going to steal this gentleman's water. I'm so sorry, buddy. Thank you. I hope you drank from it first, though. We have a 1-year-old. That's all we drink is backwash. I don't need my glasses for this. So this is the advanced photon source. This is a synchrotron. It's not like a particle accelerator like in the CERN or the Large Hadron Collider. In the Large Hadron Collider, you want to retain energy and get to tera-electron volts. You just want to conserve energy, conserve. In fact, what a synchrotron is not circular. It's a polygon. What you want to do is accelerate electrons very, very quickly and then change directions. And when you change directions, they emit a huge amount of energy in terms of photons. And we collect those photons and we use them to look at the interatomic distance of atoms in our system. My expertise is building photonic systems that are integrated inside of samples. So our sample is 1/100th of the width of a human hair. This is about 1.1 kilometers in diameter. So we're using about a multi-billion-dollar facility with hundreds of superconducting magnets that's arranged in an array of a diameter about 1.1 kilometers, probably about $1 billion of optics to look at our sample that's a width of 100th of the width of a human hair for about a nanosecond. But that's what we've got to. We designed photonic systems to do elaborate measurements. We're trying to deliver lasers to heat the samples. We're trying to use the synchrotron radiation from the ring to look at the interatomic distance of samples. And because these things are quite complicated, there's a whole bunch of additional optics that we have to build on. And it's why we have such a big team. It's a multi-man, woman contribution here. We need 10 or 15 people contributing for a couple of years to be able to pull off one of these measurements. So this is a video of an experiment that we're going to do inside of the synchrotron beam. Yeah, no volume because it's me screaming at my students. So it's going to play. So I'm going to ask you to pause it if that's okay when the time is right. This is just to give you some insight. What is this guy talking about? So we're going to stop it right here. So this is my diamond anvil cell. Inside it is a sample of water. It is a 2 million atmosphere inside of this cell. So 28 million psi. The synchrotron photons are coming through this direction. And behind all of this are detectors for measuring very, very high energy X-rays. While this is going on, we're using lasers to heat the sample to about 5,000 Kelvin. So the sample is 100th the width of a human hair, but it gets so hot, the illumination you see, so something that's the width of 100th of the width of a human hair, it gets so hot, it lights up the whole room. So when you have something glowing at about 5,000 Kelvin, it is pretty damn bright. So tungsten, which is the old tungsten bulbs, has a melting temperature of about 3,860 degrees Kelvin. When you heat these tungsten bulbs up, they get to probably about 3,000 Kelvin. We are way over this. Something so small that is incredibly, incredibly hot. And what we're trying to do is replicate the interior of Neptune. We can get to the pressures, we can get to the temperatures. We're using this advanced photon ring to try and get the X-rays we want to look at the interatomic distances and spaces between these atoms. From that, we can derive the fundamental mechanism for why these kinds of materials, i.e. water, has the properties at these interior planets. So, what are we really doing? We are trying to improve counting statistics. I wasn't going to talk about this, but you're all observable astronomers. Really what you're trying to do is improve the counting statistics of your cameras. You don't want high background, yes? You want to minimize the noise in your camera, maybe using a cooled CCD. Your whole game is signal to noise. That's what I'm trying to do. I'm just playing a signal to noise game by manipulating nature to take the best advantage I can to give me the best counting statistics I can. Water is an incredibly complex system to play with. When you crush it, it nucleates in very, very large crystal sizes. That gives you poor statistics. What you really want is tiny crystals for the same volume. By playing with the laser and messing around, what everyone else in the world sees, we're going to do the next slide. So this is the data everyone else in the world sees. It doesn't mean much to you. But I hope you can understand that when we play using our technique, these things should be rings, and they're not. We can use our lasers to generate ring-like data, which improves the counting statistics that we have. The better the counting statistics we have, the higher the precision of the modeling, the higher the determination and the likelihood of the findings that we give. So it doesn't look like much, but this took 7 years. I'm just going to show you a little bit of data for everyone. What we find, remarkably, is when you squeeze water, compress it beyond the conditions of the Earth, it actually lowers its structural symmetry, and I'm going to explain that to you. So about 100 years ago, it was assumed that when you squeeze things, everything tries to make the most compact arrangement it can. You squeeze stuff. If we all were in a room, we are in a room together, we're quite casual. If we started to bring the walls in together and made the room much, much smaller, at some point, some of us would have to move our legs and arms, and really, as the room gets much, much smaller, we would have to start to rearrange ourselves to feel comfortable. As the room gets much, much smaller, we would be very, very uncomfortable, but if we had the option, we would even move ourselves even more. Remarkably, water, what we find in this data, and I'll try and explain it to you, is when you compress it beyond the conditions of the Earth, it doesn't retain a higher symmetry order. It lowers its symmetry, and we don't understand why. It doesn't make any sense. You compress this thing, you want to put as many atoms in one box as possible, but actually it doesn't want to do that at all. It wants to go to a lower symmetry. And the way we know that is, instead of having one peak, whatever this peak might be to you guys, we have one peak. When we compress it, we start to get an array of different types of peaks. And the more peaks we have, the lower the order of the symmetry. That's the take-home message from this slide. What's confusing for us is, why would nature want to do that? Why would nature not want to have everything in the most highest order symmetry packing possible? We don't know. We take water to about 300 GPa, 3 million atmosphere. The pressure at the center of the Earth is about 3.3 million atmosphere. There's no water on the Earth past about 1 million atmosphere. So the likelihood is, what we're trying to look at here is what exoplanets, water-rich exoplanets, behave like. And by taking the data very far out, what we find is water is highly incompressible. This soft molecular system is not as squishy as you think it is. And this has significant effects when we look at Kepler data later on. When we look at the Kepler data and we look at the mass-radius ratios of exoplanets, what we find is a lot of them are most likely water-rich. What we thought were rocky systems were actually systems that most likely have water now, because water at these very, very extreme conditions is not soft. It's this weird lower symmetry, very incompressible system that's just baffling to us at the moment. So, I have no idea how I'm doing, but I'm just going to keep talking. I was interested that Bill reached out to me because I don't really give astronomy talks. I talk in chemistry departments, geology departments, physics departments. You're the first astronomy orientated community that I've looked at. But in preparing this talk, I realized actually I do a lot of work with astronomers. In fact, all the time. UNLV, I must say, and I hate to say this, but the astronomy department is the strongest department on campus. I'm in the physics department. Our astronomy department is phenomenal. We have some of the leading experts in gravitational waves, in protoplanetary disks, in the Kepler mission stuff. My colleague Carl Hayson is on the original observation from the LIGO system for the gravitational waves. I mean, they're just superstars. And as I've hung out with these folk, I've started to realize that actually a lot of the things I do are highly applicable. And so this is me taking all the stuff I've done that I've talked about in the lab with lasers and diamonds and so on, and meeting a bunch of astronomers and realizing that actually a lot of the data is probably incorrect. And I can play, when I say I mean the royal I. Me and my group and my whole community can play a significant role in allowing them to change their interpretation of their data. So how would you describe the unknown? For inside the Earth, we can't dig that deep, but we have seismic data, we have volcanoes, we have geologists, damn hippies roaming around, picking up rocks. But when we look up at the sky and the night stars, there's no way we can get to these planets in our lifetime. We have very, very limited data, and using some very fundamental rules, we're going to try and interpret what these planets and these stars and these supposed celestial objects mean to us. So next slide, thank you. So I'm going to talk about the Kepler mission. This is not Johannes Kepler. This is my colleague Jason Stefan, who's been on the Kepler mission and is who I collaborate mostly with. So he's an observational astronomer. He's worked on the Kepler mission for the last 15 years. The Kepler mission finished about 9 years ago, or 7 years ago, 8 years ago, pardon, 8 years ago. But we're still actually processing a huge amount of data from them. So I met him about 10 years ago at work, and over lunch we realized actually a lot of what I do could help him reinterpret a lot of the data that they've got. They've got petawatts and petawatts and petawatts of data that they're still churning through. I'm going to give a quote by Johannes Kepler. The diversity of the phenomena of nature is so great, and the treasures hidden inside the heavens so rich, precisely in order that the human mind shall never be lacking in fresh nourishment. Kepler was an absolute polymath. He was the assistant to Tycho Brahe, yes, who died of a bladder explosion, if you know about this. So Brahe was the greatest observational astronomer prior to the invention of the telescope. He spent 30 years looking at this night sky and tracking every object he could see. He went to the King's feast and refused to go to the toilet until the king stood up and died of an exploded bladder. Johannes Kepler, his assistant, inherited his books, his logs, and using math, basically devised the free planetary laws that we use today. A true polymath, Johannes Kepler. In fact, the third law is what we use to try and understand the observation of exoplanets. Next slide. So, the night sky is vast. The Kepler mission looked at a very, very specific field of view. I don't know if we can see it with the lights on, but it looked at a specific field of view and stationed there for a long time, just collecting frame after frame after frame. What allows Kepler to be so powerful is the advancement in CCDs, in charge-coupled devices, the same thing on your cameras. But unlike us, there's no light pollution out in space. So they can point their telescope where they want and just collect data. And what we're interested in is one of these tiny, tiny, tiny little dots here, which represents a star. The Kepler mission allowed us for the first observation of exoplanets. And these were observed by looking at stars, hotspots on the CCD, and realizing that across these hotspots, smaller celestial objects moved across them. We know from Einstein field equations, gravitational understanding, hydrostatic pressure, Kepler's laws of motion, Kepler's third law, the square of the time period of the planet is proportional to the cube of the distance from the planet to the star, or from two celestial bodies to each other. that we could start understanding that these objects moving across were most likely terrestrial systems. And what Kepler did is, by having these incredibly sensitive charge-coupled devices, is just take photo after photo after photo after photo. And when you analyze this sequence of photos, what you find is for a given spot, a given star, if you track the brightness of this star over a period of time, you get blips. You get attenuation of the brightness of the star. And this was an object crossing the star. It didn't have to be a big object. In fact, if you magnify 100 times, you can track very, very small objects. And these very, very small objects were Earth-like species, these exoplanets that were observed for the first time. So by tracking the brightness of various stars, we were able to find thousands and thousands of Earth-like systems. So if we look at the body of data collected, it's not too dissimilar like our solar system. Across these stars were very big planet-like systems, like the gas giants, but we all now know they're just giant balls of metallic hydrogen, right? Metallic fluid hydrogen. We have ice giants, but actually the bulk of the observations led us to believe that what we were seeing is Earth-like species. Mercury, Venus, Mars, the Earth, terrestrial systems, silicate-based systems that had the same size to the Earth or much bigger. And this is going to be my last slide, and I'm going to spend about 5 minutes explaining this slide to everyone. I thought about putting lots of fancy photos in, but you folks probably see much prettier things up through your telescopes than we do. So this is a very complicated figure, and we're going to hold each other's hands, intellectual hands, and we're going to discuss this figure and what our work has done to allow us to better understand the observations through Kepler. So on the x-axis, on the horizontal axis down here, is mass, and we're looking at Earth masses here. So what we care about is those objects in the sky observed by Kepler that are Earth-like. Jupiter would be somewhere way, way, way up here. So these are Earth-like masses, and these are radii comparable to the Earth. So the Earth would sit right here. The Earth would have a radius of 1 and a mass of 1. What we did with Jason Stefan's group is we went through all the data, all the Kepler data, looked at all the observational things, and picked about 100 species that we thought were the most appropriate to us. These are things like Kepler 10b, 36b. I don't know if you guys have looked at the Kepler mission stuff, but they decided to give these things all alphabet soup names and so on. What's very important here is we're going to look at a projection of what each composition of each planet looks like. So, for example, if I had a pure iron planet, which is very unlikely, I should sit on where this red line is here. If I have a pure rock planet, much like the Earth, it's not really pure rock, but it's somewhere between the iron core and silicates and so on, I sit where this turquoise line is here. And the likelihood is that a bunch of these planets sit on this turquoise line. They're Earth-like. Let's pick Kepler 10b. It has an Earth mass of about 3, has a radii of about 1.6. It's super Earth-like. If we pick something much bigger, Kepler 30b here, you can see the reflection there. Kepler 30b is a serious super Earth. It has a terrestrial composition, but it is 10 times the mass of the Earth and nearly 2 times its radius. This is a big like species, most likely terrestrial in its composition, but much, much bigger than the Earth. And before I go on, if we just take our thoughts right back to the beginning of this talk, as you compress materials, their properties change. So even though it has an iron core and is made of silicates, its properties are very, very different to the Earth here. It is 10 times the mass. The pressures are much, much higher. The temperatures are much, much higher. How it behaves is unknown, but it will be very, very different than to what it's like here on the Earth. One can crystallize their imagination when you think about what it's like to be on a super Earth. So where does our work come? So prior to our work, when we're looking at water, the only experimental work prior to us was done by Frank. This is the dotted black line here, and it's projected out over here. Everything else on this plot is theoretical. What our work did is provide a new line here. It's in black here for pure water. This trajectory here moves much higher. Because we know that water is much more incompressible, the likelihood is a lot of the observed Keplerian planets here are most likely water-rich. We weren't aware of this before. None of these planets really sat anywhere near this regime here. This was an over-extrapolation of the Frank work. We weren't quite sure what these planets were like. But now that we understand that water is very incompressible at planetary-like conditions, the likelihood is that a lot of these planets that were previously not understood well are water-rich planets. We're not sure if they're like Neptune or whether these are terrestrial systems that have a huge amount of water on the surface down to the inner core. But you know, what we found remarkable prior to our contribution to this is that most of the astronomy community was relying on theoretical calculations. And as I said earlier, never trust a theorist. We're all experimentalists in this room, yes? We all want to go and see for ourselves with our own eyes what's out there. And so, maybe a bit over-dramatized, but the likelihood is water-rich planets should be much larger than we've observed and much more plentiful in the observable universe. And so we're very excited about the James Webb program going up. We're collaborating with folks on this program. And what I really hope to show you, last slide, that's it, we're done. Or in my lecture. I'm gonna stop here. Yeah, last slide, we're gonna thank the audience. What I really hope you've all got for it is, as a condensed matter physicist who's an experimentalist who's interested in the absolute configuration of atoms to the nearest neighbors and the interaction of bonds, we can extrapolate our understanding to help astronomers understand what's in the deep space and beyond. And thank you very much for your time, and I look forward to the questions. I don't know who's invigilating. Someone needs the mic.
So, the DART mission, you talked about us seeing things with our own eyes. That one obviously was something we could all see, and it was fascinating. What, if anything, from the DART mission did you find to be the most interesting, even if it's outside of your area of research? And my second question is, if you could tell NASA, go do this experiment in space for me, and they had to do it, what would it be?
I'm going to answer that in reverse. I think about that second question every day. What could I ask NASA to measure? The folks at NASA have got their game plan down. I've read a lot of Timothy Leary. I don't know if folks have read Timothy Leary about, you know, one of Timothy, again, another psychologist from the 60s into LSD treatment and whatever, and being a complete hippie. And he talked about the effects of lower gravitational effects on human evolution and human biology. I think the real questions NASA have to ask are biology related, to be honest. I don't think these are such difficult experiments and expensive experiments. I don't think my ideas are good enough, or they're too fundamental for wasting NASA's time. But I think about that question every day, because there's calls out for it all the time. Every 6 months, NASA has a call. If you have an idea, you can just write a proposal to NASA. How do frogs mate in space? How does, if you grew a nanorod of a material in zero gravity, how would the deformation, I think about this all the time. And your first question was, what was it about the Kepler mission?
The DART mission, where we went to the asteroid and changed its
Wow.
its orbit?
Yeah, that was amazing. Math works. Math works. How amazing was that? That's just math. I tell my students all the way, it's deterministic math. You can calculate it and send a damn thing to a flying asteroid. That's a beautiful example of deterministic math. Yeah.
Okay, cool. So I'm going to ask, they're not gonna be super serious. While doing the presentation, I had like so many questions pop up in my head. So I'm going to ask like the less serious, the quicker ones. So while you're going through your presentation, you mentioned that Jupiter is a metal fluid, right? And often in classes, in astronomy, physics classes, whatever, they've told me that you can't actually land on it. So do you think because it is a metallic fluid, you can land on it now? Or would you just like sink?
So we've sent, we've had a few flyovers, Voyager 1 and 2, and we have crashed things into Jupiter, but absolutely not. I mean, once you go past the hydrogen atmosphere, the pressure and temperature start to get very, very high. I mean, can a human land on it? No. Can a robot land on it? Probably not. It's not in our lifetime of technology. And at some point, I mean, a better question is there a clear transition? Is it gaseous? Is it liquid hydrogen and you walk across this barrier and then it's a metal? Or is there a progression of it becoming metal-like? I mean, let me give you a good example. You know, Elon Musk has been talking about going to Mars for God knows how long. The likelihood is we're not going to do it. These are not trivial missions. It's very easy to say something, but these are incredibly complex missions. To send a human somewhere and are they going to come back? Most likely not. And so I can't answer that, but I can't imagine it. I hope for my children's sake or my great-grandchildren or whatever, that it's a possibility. But in our realm of imagination, no, I don't think so.
I have one more question. So do you know if metallic water is safe to consume and will it be sold in Walmart?
Yeah, I definitely wouldn't drink it. No, absolutely not. I mean, the existence of metallic water will probably be about 3 million atmosphere and about 6,000 Kelvin. If you could hold it, it would just burn through you and fall through you. These are things that the human mind can only imagine, but are outside our reality. Definitely don't drink it.
Not a cool marketing thing, though.
I had two questions. One, you were talking about the free energy back at the beginning, and going in the opposite direction here pressure-wise. But on Pluto, there are, they say, mountains of water, but they're hard as granite.
Right.
So as the pressure goes up, does the free energy go down, and so that granite ice on Pluto, does that actually have more free energy than ice here?
So I'm not an expert in Pluto. The likelihood of Pluto is that on the surface is just ice. It's just the normal ice you'd find here on the Earth. If you start to go into its interior, the pressure is probably not that high. It's most likely like the ice 7 that I showed you, in that you probably don't remember, but one of the lower pressure ices. I would expect the ice on Pluto to be very similar to some of the Jovian moon ices. It's probably comparable in size, and it's the size that defines the amount of material that defines the pressure, and it's the pressure that then complicates the free energy landscape.
Well, just in general, more pressure is less free energy?
Yes.
Okay.
Yeah.
And then my second question was, when I started studying in astronomy, they said that Jupiter probably has an Earth mass solid core.
Excellent question.
But then Juno, the Juno mission, they were saying it may be dissolved in the center of Jupiter. What do you think?
A great question. I'm glad. That's what I'm going to be working on for the next 5 years. So this is the question. So how was the solar system formed? Well, our star was formed in some kind of star factory and migrated out to where it is here. And a protoplanetary disk emerges. This protoplanetary disk has all the elements you need to make up a solar system. and the gravity of the star pulls the protoplanetary disk, the composition towards it, the material towards it. The first bit is that most likely something the size of the Earth or bigger, i.e. Jupiter's core, emerges, and this sucks part of the hydrogen and helium towards it, and then the formation of Jupiter is formed, and then so on and so on. The question now is silicate, rock, soluble in metallic hydrogen, fluid hydrogen? Yes, most likely. In liquid metallic hydrogen, the likelihood is that silicates are soluble, and if they're soluble, then Jupiter shouldn't have a solid core. Its core should be dissolved into the liquid metallic hydrogen coming outwards. We're going to find out. We're going to put some rock, bridgmanite, FeMgSO3 into my diamond ample cell, put some hydrogen, go to 5 million atmosphere, zap it. I'll come back in 5 years. These experiments take so long, but that's a great question. Something we talk about a lot over beers at work.
That was a great presentation. I have 2 questions. One of them is, you said there's 19 states of water.
Yeah.
How many of them are solid, how many of them are liquid, and how many of them are gas?
Great question. There are 19 solid phases of water, but is that true? I don't even know. But there are different states of liquid water. There is low density water, high density water. Of the 19 states of solid water, not all of them are solid-like. Some of them are amorphous, and there are amorphous transitions in water itself. It's very, 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 very complicated. In the gaseous state, we think there's singular states, but if I'm going to just rev my science engine right now, there's something called the Finkel line and the Widom line, where there's a separation within fluid states based on shear velocities. So when they talk about fluid states, actually there's probably phases inside the fluids phase, maybe inside the gaseous phase. But this is hardcore condensed matter physics. That's outside my realm of expertise.
Thank you.
That's okay.
And then my next question is about the diamonds that you use in your DAC. Can you reuse them? How big are they?
Great question. Great. They're about 1/3 of a carat. So when I was a grad student 20 years ago, we would have a diamond dealer come to our lab with 100 diamonds. I would test each one and collect maybe 1 or 2 for the experiment. Because diamonds were only made by Mother Nature in volcanoes, in the deep earth that was spat up by volcanoes. But now you can use a technique called chemical vapor deposition. You can basically buy a microwave-like system and grow a diamond. A really quick story. I was in Spain with a friend, and he threw me something about half this big on the train, and I was like, what is that? And he was like, oh, it's a diamond. He'd grown it in his lab, and I was like, we're gonna get robbed. And he was like, no one would believe you right now if you went and told him this was a diamond. He grew a diamond that big in his lab. So we can manipulate nature to make diamonds in-house, which are better than anything Mother Nature can make. So the diamonds we now have in my lab, they're about 1/3 of a carat, and they're absolutely flawless, better than anything Mother Nature could make. Can we reuse them? That's a wonderful question. Unfortunately for the high pressure experiments, no. We break about $100,000 a diamond a year in my group. Most of your federal tax dollars are going to pay for my diamonds. It's a very expensive hobby. For low pressure stuff, you can reuse them, but when we're trying to replicate the interior of planets, diamond becomes plastic. That's how hard we put the strain rate on the tip of the diamond. It goes from a diamond is incredibly rigid thing, undergoes elastic to plastic deformation, and I should have bought some broken diamonds and just handed them out. They belong to the taxpayer. We can't get rid of them. I have a safe in my lab with probably $1 million of diamonds, but they're worthless. I mean, yeah, they're worthless. So.
Great presentation, thank you. Quick question around that really dense chart that you showed. It looked like, and I might be misinterpreting it, but it looked like the error bars on the pure water planets and the 50-50 planets overlapped. And I was wondering how you break that degeneracy, or can you do it with mass and radius alone, or do you have to have some kind of atmospheric spectrograph or something?
Amazing question. Chris, can we go back a slide? Boom. So the question is, I'm going to assume we're talking about the 50% water rock ones, yes? Yeah, so the first thing we're trying to do with Dr. Stefan's group is trying to reduce these error bars. Can we reduce the error bars? It's hard to differentiate with such a large error bar what its likely composition is, but we're just playing an averaging game. We're going to assume that this cluster here is one component-like system, and it sits pretty close to our extrapolated line here. But you got to remember, just put a caveat in this, the likelihood is nothing is really pure water. It probably has ammonia, it probably has methane in it. It's probably a multi-component system which will move this line, and as we reduce the error bars and move this line, eventually there'll be some accurate convergence, which we're quite off at the moment. That was my hand wavy answer to that.
So you said that you're making things that nature can't.
Yes.
Which is amazing. And I can't help but notice that since so much of it is actually metallic, that there has to be industrial or maybe like the computer manufacturers of various kinds that would be very interested in some of these very unusual metallic objects. And also, I would like a diamond bowling ball, please.
you probably, I hate to break everyone's heart here, but diamond will probably be worthless in the next 30 to 50 years. It's what, you could just grow it in you could probably buy a machine that presses a duck ball and grows you a diamond bowling ball in the next 20, 30 years. Put your money in precious metals. So the dream is to make a material that has functionality for everyday use devices. Unfortunately, most of these materials exist at very, very high pressures. And when I show you that first plot of reducing the pressure, not all of them are recoverable. A lot of them back transform into their prior state. Like hydrogen. If you make metallic hydrogen and release the pressure, it just back transforms into something that looks like glass. And also, furthermore, the sample sizes are very, very, very small. But I'm going to tell you a secret here. I'm actually a chemist masquerading as a physicist, and my background is actually in organic chemistry, and then physical chemistry, and then high energy physics, and low temperature physics, and high temperature physics, and now I'm doing this kind of thing. So somewhere deep inside my core is that chemistry thing, which I'm trying to make materials that are functional. Yes, that's the dream. Because we really can make materials that Mother Nature cannot make. We do it all the time. There's no evidence of it in nature anywhere.
Thank you so much.
Yeah, just the coldest place in the universe, MIT. Coldest place in the universe is MIT. Maybe Gila in Boulder in Colorado now. Maybe it beat the record by a billionth of a Kelvin. But the observable universe is 4.2 Kelvin. Nothing's really colder than that in the observable universe. In Gila or MIT, it's a billionth of a Kelvin. So we are amazing as a species.
One more question.
When you compress hydrogen down to the metallic state, do you end up with a lump of protons and then the electrons floating around on the surface?
Amazing question. So what you've just described is something called an electride. When you get towards neutron star densities, what happens is that the protons hang out together and they're so packed, there's no space for the electron orbitals to exist. And so the electrons dissociate from the nucleus and form their own cluster away from the nucleus. We've observed this in certain materials experimentally. There's a huge amount of theory under this. It's called an electride state. In metallic hydrogen, no. Metallic hydrogen is even more complicated. I'm a proton with one electron. My nearest neighbor is a proton with one electron. I have to have a bond with my nearest neighbor. So there goes my one electron to fill up my 1s orbital. But I need an electron in the conduction band to be a metal. So how can I form a bond with my nearest neighbors and have an electron in the conduction band to be a metal?
But you don't have any neutrons to help.
That's right. That's right. And so the metallization is not an interaction of the nucleus wave function, but most likely an overlap of the electronic wave function that smears out to be a continuum that gives you that sea of free electrons.
Thank you, sir.
Brilliant. Thank you so much. Thanks for coming out. Thanks for hanging out
There's
with
one
us.
more question, Bill.
We got one more? Okay, one more.
Another source of diamonds would be some silicon carbide. For example, you have silicon carbide on gallium nitride process for mimics, and you could possibly use that as a option for diamonds. Man-made.
So marcasite, the silicon carbide compound, none of them are incompressible or as hard as diamond. Diamond is 10 on the Vickers hardness and has a bulk modulus of 440. No other material comes as close to the incompressibility of diamond. And so if you want to go to planetary conditions, you want to put the most amount of strain on the material, and nothing beats diamond, not even close.
Okay, thank you.
All right, thank you so much.
Cool.
Okay. I don't know about everybody else. Anybody else, before we go to the main meeting and the elections, need a break? Huh? I know Bill ran for one. Really? Nobody in here wants a break? Exactly. You know? I mean, really, guys. Shall we take a break? Shall we take a break? Shall we take a break? Okay, hey, you know, after today, I'm gone, so I'm going to put it to a vote. Do y'all want to do the raffle and then a break, or you want to do a break and then the raffle? Okay. Break and then raffle? Raffle and then break. All right, break. Come get your raffle tickets if you don't have them.
With the presentation of the physicists that came in and talked for a while. Now they're just doing a raffle and stuff, but I can put the speaker on there if you want to watch.
No,
All right,
that's okay.
we're gonna sit down. We're gonna.
It's just after you're all done, I need you to help me with some.
All right.
Who's got the other mic that's talking? Because we can hear you. Oh, I don't know. I heard discussions going on anyway. Okay, we're going to get the raffle going, get it out of the way, then we'll hold the election. That's kind of been where I'm being led. Anyway, it's a good idea. So, okay, I got to pick the doomies. I've been getting a lot of flack for not picking the right tickets. There we go. How about 155449?
Where's the raffle stuff? Here, right here. Add this thing to it.
Oh.
It's junk.
Okay, we got a piece. I won't repeat what he called it. Anyway. Hey, 449.
Right here.
All right. By the way, I have a neat little camera that monitors and you can see it on your phone and all that cool stuff. I have one of those tripods. It's not worth much, but it will hold a little remote camera you can put on it. All right, let's go to the next one. I usually grab a handful and then filter out one, so we'll see. 155421. 421. Yay, we got a winner. That's okay. I trust you. You're good. 155453. Better than last month. I mean, they were running a string. Okay, we got a winner. Oh, I ought to put this one back. It's bent. You know, people used to bend their things and get it drawn more. I don't know. We'll see. 155397. One 155397. There we go. All right. How many more things we got? Let's see. It's still got a tripod. That's a good idea. I got about 4 of those I'd like to bring in. What? 155424. 424. No, I haven't seen anybody leave yet. So, okay. One more time. 155424. If you discover you got it, let me know. You come up here. All right. About 155448. 448. Hey! Oh, no. Numbers are running a string. I got to shake them up. Okay. Oh, come on. 155411. Whoa! Well, at least the same person's not winning all the time. Yeah, put it out there. No. In there. Okay.
Are these a set or separate?
Well, were they laying as a set or were they laying separate? What?
They're a set.
It's a set. Hey, what do I know? Guys, remember, I'm a photographer, all right? You got to guide me. I don't know this stuff. I just shoot pictures. 396. 396. Hey, there he comes. Yay. How many more we got? Oh, we got a few. VP, tell me when my time's up. Okay, one more. 155423. 155423. It's last ticket, guys. Last one. Well, maybe not. Okay, we got to have one more winner. One 414. 414. Hey! All right. So we'll save those for next time. Hey, we did pretty good. Okay, where are we? Election. Can we get that election slide back up? It's back at the very beginning. Okay, go. That's it. Keep going. I think it's that one. All right, here we go. We're going one by one, by the way, guys, as we're doing. We've and we've determined what the policies and what the procedure and everything else is supposed to be by the bylaws, which we've been kind of getting by. But anyway, we're going to correct that. President, is there anyone in here or on Zoom at this time that wishes to have their name added to the ballot? Okay. I didn't hear anything from the Zoom monitor, so we're going to go with that. All those in favor of Cy, by the way, I am horrible with last names, but I'm going to follow the same procedure for everybody. Cy S. As president, raise your hands or say aye. Okay. All right. Zoom, you need a minute to get the count. Oh, we didn't take a count here. It's kind of unanimous. Okay. All right. We good? All right. Okay. Okay. All those in favor, Vice President Bill H. All those opposed? Okay. It carries. Welcome, Bill. He will carry through, as you know, we all wanted him back anyway. So, all right. For secretary, is there anyone in the room or on Zoom that wishes to have their name added to the ballot? Okay. As procedure and protocol, there are two nominees for them. We need you two to leave the room for the vote. My lawyers have spoken. Down here, down the hall, the first floor, down through the stairs. Yeah. Oh, do y'all want to say anything? I'm sorry. Okay. Whoever wants to go first. Ladies first. You want to have something to say? No. Do you want to say something? I can. Okay. Vote for me.
Yeah, vote for me. No, I've served the club for about 14 years in various roles and would be happy to serve for you for the next year as the secretary.
My name's Bob Circus. I am running for secretary of the Fort Worth Astronomical Society. I've been a member since about 2010, and I like to give back to this organization because it gave me an opportunity to spend quality time with my youngest son, Jake. He wanted to learn about astronomy, and that's why we joined, and before he went off to college. We had some tremendous experiences to the club because of this club, including building telescopes and doing outreach. So that's why I like to give back to the club. So that's me. That's why I'm running. And thanks.
Thank y'all. Okay, for this one, I guess we're going to have to take a count, make sure we get it right. So okay, I hear noise over here. I got to stop and listen. Secretary, Michelle T. All those in favor, raise your hands. Take a count. Secretary is counting. Keep your hands up, please. You got it? Okay, for Robert S., all those in favor? Okay. Give you what? Okay. We're going to take a minute for her to. Well, she got them.
Chris was giving me the Zoom tally as I walked
Chris was he.
I now need to count the ones that I got.
Yeah, we have mail-in ballots too that were sent, both email and mail-in. Hey, just you know, whisper. Okay, we'll move on while she's counting. Let's go ahead to Director 1. Anyone wishes to add their name, either person or Zoom? What? Whoa. No, never mind. This has been taken care of. Forget it. This is Director 1's been taken care of. He is Director 1. And the board nominated him. Yeah. Yeah, the board appointed him at the board meeting. So he is Director 1. Director 3, Mark K. Okay. Is there, well, okay, I jumped ahead. Is there anyone wishing to add their name to Director 3 on Zoom or in person? Now let's take a vote. Director 3, Mark K. Raise the hands. Also acknowledge on Zoom. I think we're good. Okay. Welcome, Mark. Oh, those opposed? Yeah, those opposed. I'm sorry. Those opposed, I got to follow procedure. Okay, now I can say it. Congratulations, Mark. Director 4, anyone on Zoom or in person wish to add their name to the ballot? All right. Director 4, Tom S., all those in favor? All those opposed? Hey, there's hands up, Tom. Okay. Welcome, Tom, to Director 4 position.
The other thing is this ballot doesn't have Constantine on there, but he does need to be voted in for treasurer.
Okay. One's not listed. I was informed that's, you know, I go with what's pushed in my face. Anyway, one needs to be recognized and voted in. Constantine is running for treasurer, unopposed. Does anyone wish to add their name to the list? Position. Constantine, I'm seeing everybody shake their head no. Anyway, all those in favor of Constantine following through with our treasury? All those opposed? Sorry, man. Welcome as our next year's treasurer, Constantine. I just wanted to add an extra note. When I got this position, these two made it possible. I tried to quit 3 or 4 times, they wouldn't let me. Anyway, what do we got?
Michelle won, so invite them back in and make that announcement.
Okay, Michelle won. Okay, come on back here. Okay, so would y'all welcome our new secretary, Michelle? Now what? Okay, that's over, this over. Bill, what's in the sky, I think? Unless I missed something. Hey, there it is. I did not miss anything.
Okay. So this is everything for the next month until the next meeting. Ironic that tonight's like one of the first like beautiful. What? I'm sorry, what? Oh, the swear-in? Do we got to do a swear-in? Yeah. Okay.
I understand that's not my job.
Okay.
We need all the waiting candidates to come forward to be sworn in, please.
Cy Simonson, Konstantin Bakentas, Bill Hall, Michelle Thiessen, Mark Kwasowski, and Tom Schneider, please. Okay.
Thank you, Cy.
Officers-elect, the members of the Fort Worth Astronomical Society have shown confidence in your abilities by electing you to your respective offices. I now ask each of you, do you accept the office to which you have been elected? If so, answer, I do. Please raise your right hand and repeat after me, and I'll go very slow this time. I accept the office to which I have been elected. I will perform the duties of that office to the best of my ability and will in all my actions strive for the good of the Fort Worth Astronomical Society. I will uphold and enforce the club's bylaws and will promote the purposes of the Fort Worth Astronomical Society. All of this I now affirm in the presence of the members assembled here. Please lower your hands. Officers-elect, I now install each of you into the office to which you were elected and charge each of you to be faithful and diligent in discharging your responsibilities. Ladies and gentlemen, the elected officers of the chapter have been duly installed for the next term beginning July 1st. Will you please join me in a round of applause? Okay, you all get to work at your jobs.
All right, back to the space things. So I guess we really don't need dark, do we now? So I'll stay right here. Next slide. This is Stephen Kennedy's most recent work of art. This is Barnard 150 out of the Barnard Dark Nebula catalog. Next slide. Very nice, by the way. So bright comets this month. So 10P, Temple 2, it's getting brighter. It's in Aquarius. It's going to continue getting brighter as the next couple of months come on. 220P McNaught. So this was actually a real surprise for everybody. Yes, it is dimming. It's dimming now, but it went through an outburst. Go to my next slide here. So this is actually a chart of what happened with McNaught not too long ago. So something happened. Fresh vent opening maybe, sinkhole, newly exposed volatiles, could be a chunk broken off, could be a landslide, it could be a comet breaking up. But what happened was we had Comet McNaught go from about magnitude 18 to magnitude 8. And we're talking about a brightness change to the factor of 10,000 times brighter. So something happened on McNaught 220P that made this happen. So this is kind of been the the big deal with the comet freaks. Next slide. Is there a term? I don't know if there's a term. Occultations and close approaches. So Wednesday the 17th, tomorrow, the moon occults Venus. It happens in the day, but those things are easily visible with the binoculars, the telescope. And Saturday, July 4th, pre-dawn, Mars and Uranus are at an 8-minute separation. This picture right here is our own Scott Ripley's shot of the transit across the sun. You see the little guy right here? That's the International Space Station in front of the sun. So that happened on April 4th. Next slide. So it's turned into a bit of a joke, but the thing is that every once in a while a date comes up that's actually a prediction based on brightness changes and different measurements as compared with previous occurrences of the nova that actually set this as June 25th, 2026 is their next best guess for when this thing's going to go off. So we'll see if that happens, but it's got to happen because historically it's been happening. These things don't just stop. So we'll see what happens. Next slide. And our summer solstice, which, if you remember, is Latin for standstill, which is basically as the highest that the sun gets during the year, and then it sits there for a couple of weeks, and then it comes back down towards the winter. And June 21st on Sundays when it reaches it, and the sun is straight up in the sky if you're on the Tropic of Cancer. So there you go. Next slide. Asteroid 152637, 1997, NC1. You've heard of it, right? You've heard of it? You've heard of it? No, nobody's heard of it. So the thing is that it's coming actually quite close. We're talking about lunar diameters right there. So 6.7 lunar diameters, which is 0.017 and some change AU to us on Saturday, June 27th. And it's going to be about magnitude 10.1 at its brightest. It's somewhere between 710. Am I getting you with that laser? Do I need to be careful about that? Okay, yeah, sorry about that. I'll hold it down here. 710 to maybe 1,600 meters in diameter. Not a planet killer, but definitely would cause a little bit of damage. But it's not going to happen. But you know, like I always feature with these things, you can actually see the motion when you just sit and look at it. So it's pretty cool. And here's the map that kind of shows it. It's going to be going through Ophiuchus. Next slide. June's full moon is on Monday, June 29th. Next slide. It's asteroid day again. So it's Monday, June 30th. So what Monday, June 30th celebrates is actually the anniversary of the Tunguska event that happened in Siberia in 1908. So 118 years since that happened. So maybe it was 1908. That's my math. Next slide. So the explosion was estimated as the equivalent of 5 to 10 megatons of TNT. Now, I want to give a little perspective to that, is that Nagasaki was actually a bigger bomb than Hiroshima. And Nagasaki was 21 kilotons equivalent of TNT. So we're talking about 5 to 10 megatons of TNT. If this happened over a major metropolitan area, it would be horribly disastrous. It knocked down about 80 million trees in a radial pattern from the epicenter of the explosion, which happened in the sky, and wiped out probably about 830 square miles of forest. The guy, Leonid Kulik, he's actually the guy that went out there. He talked Russia into funding him to get out there. Didn't get out there until like 13 years after the event happened, and he took all these pictures. And he's the one that's credited with really. Oh no, sorry. 19 years later. This is what things looked like 19 years later. This right here is what they. I can't remember what they called it. It was something forest. But these trees that are standing up, so these were trees that had branches and stuff, so it's nothing but trunks. The explosion happened right over this area. So basically the blast actually knocked all the branches off of the trees and left nothing but the trunks. Everything else from outside of this area was basically with trunks just laid over. Next slide. It was estimated to be only 130 feet in diameter, wiped out, incinerated millions of animals, and just caused this incredible destruction that actually still has scars on the land today. The area that's actually around where the explosion happened, nothing grows. So next slide. So, happy asteroid day. Next slide. Okay, so number 8. This is the 8th asteroid discovered. This is number 8, Flora, and it's going to be closest to us on Thursday, July 9th at magnitude 9. This was actually discovered by John Russell Hine. It was his second asteroid after just 2 months before he discovered Iris, number 7. Next slide. Next new moon is on Tuesday, July 14th. This is a nice crescent picture from Glenn Fraser. Next slide. Okay, so I'm going to feature Scorpius tonight. So it's it's one of the 48 of the original constellations that Ptolemy had cataloged in his second century Almagest. And it was they actually, historians say that it was 5,000 years ago, the Sumerians were actually referring to these stars, pretty obviously, as a scorpion. 19 named stars in it. Next slide. So it's a big constellation. It's bigger than you think, according to IAU. There's a bunch of big space up here near Ophiuchus, but there's nothing really going on there that there is to talk about, so we're going to focus on this part. So we've got U Scorpii. So this is an eclipsing binary system. It actually contains the fastest known nova. So this nova actually occurs about every 10 years. The last one happened in 2022, and it goes from magnitude 18 to 7.5 in like a matter of hours. So next slide. And then there's New Scorpii. This is cool. This is really cool because there's, from all the known septuple star systems. This is one of two known. Okay, the brightest star, it's also known as Java. It's only one of two known septuple. The other one I think is in Cassiopeia. The combined A and B and C and D components can be resolved into two stars, but the other subcomponents are spectral binaries. What I mean by spectral binaries is that they can identify only, they can't do it optically, they can identify only that those stars are actually binary systems because of red and blue shift that they see when they observe the light of the system. Next slide. So this is a spirograph brought to you by New Scorpi. I had AI do this. I actually put in the parameters into Copilot, and it gave me this. So this is a wacky thing that's going on. Obviously, it's not to scale. A and B and C and D are much further apart than this. But what you've got here is you've got AA and AB orbiting each other, and then you've got AC orbiting with AA and AB around a barycenter, which is a common center of gravity. Now, you've got that going on, and then you've got B out here that's orbiting that whole system. So you've got a system within a system within a system. DA and DB is the same thing that's going on with AA and AB here, but you've got C that's slowly orbiting around that, around a barycenter. So barycenter is going to be, wherever the center of wherever the center of the gravity is, how it's orbiting. Basically, it's got mass with these stars and mass with this star, and somewhere in the middle is that center of gravity. So that's actually the orbital center. So yeah, pretty cool, huh? I actually loaded this in there, which is something that you can pick off the internet and stuff. And I actually loaded this in. Copilot actually asked for this, and it was like, yeah, I'll do this, and it came out with this. Pretty cool. 7 stars. It's rare because to actually have 7 stars actually function and persist in a system is very difficult because obviously it's very complex. Next slide. The blue horse head. So this is actually this is a reflection nebula in Scorpius here. It's very blue because reflection nebula, dust that's in the nebula reflects and scatters blue light. And when this is Stephen Kennedy's picture. Next slide here. It's up here, by the way. Nope, wrong way. So this is Stephen Kennedy's beautiful picture of the blue horse head. And guess what the eye is? It's Java. So I bet you didn't know that, Stephen, that you actually imaged you didn't even know that there was a septuple star system right there in the eye there. So fun fact for you. Next slide. Messier 4. So there are a few Messier objects in Scorpius. It's the closest globular star cluster to us. Thanks for coming out, guys. It's closest globular to us, and it was the first globular to be resolved in the stars, likely by Herschel, who else? And there's an unseen excess mass in the center of the cluster, and it's presumed to be a black hole, which is pretty wild. Next slide. This is Christopher Ashford's image of Messier 4. Next slide. Messier 6 and 7. I kind of put these together because they're, kind of close together here. 6 is the butterfly cluster. 7 is the Ptolemy cluster. And there's a lot of open clusters in Scorpius because we're actually looking towards one of the arms towards the center of the galaxy. So there's a great deal of star formation that's going on there. Next slide. This is Christopher Ashford's picture of Messier 6. And next slide. This is 7, Messier 7. Next slide. You can see how dense the star field is there. It's awesome. Messier 80. So this one has actually a really high population of blue stragglers. And blue stragglers are very hot, very large blue burning stars that scientists really presume that the reason why these stars even exist is because of the density of globular clusters, the density of stars in globular clusters, that there's going to be collisions. And so this is what they presume, is that blue stragglers just may be results of star collisions that have just absorbed into one. Next slide. This is a Hubble shot, Messier 80. Next slide. And then there's the Scorpius-Centaurus OB association. By the way, OB is like the type of stars. They're mostly O and B type stars. It's the closest OB association to the Earth. It's got over 430 members, and the association basically means that all these stars are moving in the same proper motion. And it is bigger than just what's going on in Scorpius. This goes down into Lupus down here. So it's a pretty good swath of the sky right there. These stars have not just the same common proper motion, but they've got the same chemistry and relatively the same ages. And this association produced supernovae that actually produced what we live in, is actually called the local bubble. Next slide. And those are some highly processed stars in that association. Next slide. The cat's paw, so this last one. It's also known as NGC 6334. It's a very, very productive stellar nursery, actually one of the more prolific ones in the Milky Way. Next slide. And it looks like a little kitty paw, so actually very well named. And a good size, hey now, and a good size and a good magnitude, so it's actually a pretty one to look out for. Next slide. So that's what I got. You know the spiel here. I've got some deep sky objects. There's 64 main ones that you'd have there in that would be for us, and not like a space telescope or something. And more about that is in Constellation Guides. It's a lot of my source, so is Wikipedia and other places like NASA. So for more about Scorpii, actually the AVSO, that's the American Association of Variable Stars, actually has a really cool thing about Scorpii. And more about blue stragglers, check out this right here. This is actually a really great article about it. Next slide. So, Christian Senzik took, we'll start paying attention, right? Christian Senzik took a picture of the moon and Venus here. Pretty nice shot there. And Pan Klopfer took a picture of the sundog. And hey, if we can't see the sky, then we'll check out the clouds, right? Keep looking up.
All right. As always, my mind just, oh, good, I got to get that. Oh, the clouds go away, I could get that. All right, next slide. Business meeting, financial report. Constantine.
Thank you, Sam. Do we have the report available? There we go. Okay. Current balance is $48,843. Our biggest income was basically membership renewals. As you know, May was our renewal month, and we had 128 members joined last month. Let's look at the bottom of the page. I want you to notice that we were able to make another loan payment, and that our current loan balance is down to $978. So we hope to be able to pay that off after we have our next star party out west of here. Any questions on these numbers? Any question about finances? Let me go ahead and move on to the next page, which is membership. I just wanted to give you all an update. This was prepared, I guess it was June 6th or 7th, and it shows that we have 56% member renewal so far. That's incorrect. There was a third email that was sent out encouraging people to renew, so we're now up to 65%. It is June, so theoretically it's passed, but we will continue to accept membership renewals through the end of this month, and then in July, we will issue an email saying that if we don't receive your renewal, then you will be removed from the system. So if you are here and you haven't renewed, why? It's That's right. Any questions? Yes. There are student discounts, yes. I believe it's $30.
Are you a student?
Yes.
Technically, I'm a university, so.
Thank you so much.
We know that. Okay. Executive board update. My week's been crazy. We had a really progressive board meeting of just a few items. All my notes, my cell phone, and everything else is at home. Funny thing is, the only two things I can remember is a massive list from Chris of what we need to work on next year. Not my problem. Okay. The other thing that sticks in my mind is that the rolling building project for Rising Star was put forth to a committee to get started and get started doing the planning of what's going where, what's needed to be done. In other words, we have taken action, the board has approved for action to be taken to make that real. There were a couple other things, but what were they? That's, yeah. Those were the two that really stood out. God, I know there's a couple. Chris Ashford to purchase some pins. It's interesting that I'm a snow skier. I skied for about 18 years. Chris still skis. His wife still skis. And one of the things that draws skiers and other members, because I was a member of Corvette Club for a long time, to get participation and to get people to log in their hours is not dollars, it's not trophies, it's pins. Little pins that you can pin on your shirt or your jacket. And they seem to be the item that are held on to the longest of people that do activities across any hobby and any sport. They're not very expensive, which doesn't cost the club a lot of money. We can print a reasonably small quantity, and we can have pins for your participation. So the biggest thing that we need to do for those of us that go to Stark parties, volunteer for events, things that the club puts on that you volunteer for, if you will post those hours, then when you reach a level, you're not in competition with each other. It's not the highest one this week that wins. No. When you reach that level of how many hours that you participated for, you'll get a club pin. And you do it again, you get another club pin. You get one for 2026. Next year, let's say 2027. So the big push is, we have a lot of members that volunteer and go to Star parties. We do. Get online, get in the program to start logging your hours. Now, that helps the club to show others nationally how much we participate within our club. So it's a win all the way around. And that was voted on to fund, what did we fund him? We funded him a little bit, not much, to get the first set of pins going and to start, because we've already got members that we've got to hand pins out to. Anything else I missed? Oh yeah, that was the one that was in my mind I couldn't just pull up. Tom brought forth the proposal that we needed an emergency plan for rising star. So, I don't know. Will you give me the mic back? Once I give him the mic, he wants to keep it. Come on, Tom. He will do better than I will. Come on, up. Yes. No, we're going to do it at the end.
All right. I'm Tom Schneider, and I'm now one of the directors, but I'm also in charge of RSOA. And one of the things that was told to me before Bruce died was one of the things I needed to do was to check the first aid kit. So I pulled up the document and I started looking at this, and I went, oh my God, I totally forgot about that. So I was really thinking about what we needed. And the thing I'm really worried about out there is, hold on a second, is a heart attack, a serious bleed, or a stroke. So we're going to have 2 first aid kits. This is the one I got for one of the buildings, and I'm going to take some of the stuff out of this and put in another kit, because this is for 25 people. So there's a lot of bandages and stuff, and basic stuff. Bandages, there's some eye wash, just normal stuff that you normally have in a first aid kit. The other things that we're missing that we need in there are going to be trauma shears. So I'll explain what we're going to use those for in a little minute. Yeah. There's a tourniquet for a bleed. It's just like a big wide rubber band you wrap around. And wide and not so wide Coban is that material that you can hold bandages with that sticks to itself. And a CPR mask.
You want me to hold something?
Yeah, well, I got it. Just open it up. Yeah. So basically, this is so you don't have to put your mouth on somebody if you're doing CPR. Pretty self-explanatory. You open it up, pop it open, and put it over their face. How many people here have done CPR? Okay. Okay, you've actually done CPR on a human. Wow. Okay. So the reason for this is I was talking to the people out at Cross Plains, and the EMTs out in the rural Texas, they have 10 minutes to get into town to get to the vehicle, and then they respond. So we're looking at 15 to up to 30 minutes for somebody to arrive. So in the case of a heart attack and you have to do CPR, it's kind of ugly, it's hard, it's stressful. First thing you do is you call 911 before you do anything else, and then just start yelling for help. If the person's on the ground, don't take a lot of time to check and see if they have a pulse. A lot of times you won't feel it. You're just taking a lot of time. It's really important to start CPR. And when you do the CPR, you need to try to wake them up, slap them, shake them. If you don't wake up right away, then go ahead, tilt the head back. If you have the mask, fine. If you don't want to wait and put the mask on, tilt your head back, start doing, 30, it's basically 30 compressions, 1 breath, okay? So the object of that is to keep somebody alive neurologically in the heart until they can get shocked. CPR will not restart the heart, but a shock will, okay? The other thing associated with that is the air ambulance, and I know some people in the group have already gotten the air ambulance coverage. The one that covers us would be Life Team, and they're part of the Air Medicare network. It's $99 a year, and if you're over 60, it's $80. And that basically covers all of North Texas and Oklahoma. It also covers you inside the city, or if you're on the way, if you got in a car accident. I'm trying to go really fast here. We're also looking for a defibrillator to put out there for the club because of the time it would take for somebody to respond. So CPR within 3 minutes and defibrillation within 5 minutes is one of the strongest predictors of survivability over 60 days with good neurological function. Okay. The other thing I wanted to talk to you about was about June 20th and 21st. Some people are going to be out there Friday night. please fill out the poll if you're going to go so we know how many people are coming. There's going to be solar viewing from 4 to 6, and then I'll start a thread tomorrow on potluck, who wants to bring a dish. Let's see, right now I looked at the forecast on AI. It's kind of iffy because it's so far out, but we're looking for better data on Thursday, low, mid, and high clouds, 850 millibar relative humidity, and precipitable water, which is what caused all the fuzziness. So hopefully we'll have something out. I can put up something in a day or two. The other thing we're looking at is in August, the Perseid meteor shower will be on the 12th to the 14th. It'll be a new moon. And so I'm looking at possibly doing another event out at RSOA the weekend of that Perseid meteor shower. Okay. Sorry it takes so long.
No. You can train them later. Yeah. Okay. All right, moving on. Cy, yeah, have any? No, got nothing. Okay. Any other business? Yes, sir. Okay, hang on a sec. Question about CPR, Tom.
Question about CPR. Is there any thought to being given to maybe having a session for people who are interested in learning how to do CPR?
Yeah, I was going to ask that, but you were rushing.
Yeah, absolutely, but I was rushing him. We're not training anybody tonight. We're trying to get through the business meeting.
We can do that.
So,
People want to do that. I'll put a poll out. If people want to do that, you set up a class.
Absolutely. We'll be training and putting out notices and so forth. But that wasn't the intent tonight. Was to let you know that we're working on that, and we want a plan out there. Okay, no other business. Let's move on. Slide. Financial report. You already gave that. Okay. Again, next one. That's the same slide. Oh, yeah, okay. I used to put these things together. Now, I don't have to anymore. Okay. Again, next slide. And next slide. Monthly report. Any, let's see, announcements. Okay, I guess it's the next one. Three Rivers is coming up. September 4th, 5th, and 6th. Get your name in. This is really, really good. I've been there twice. Hopefully I'll go again 3. You've got astronomy campus owned by Texas Tech University, approximately 3-hour drive from DFW. It's a little ways out there. You have to reserve the weekend. The club has to reserve the weekend. We use members can bring their own equipment. We will also have 2 or 3 volunteers running the campus scopes. They have some big scopes out there, but they're not going to let amateurs handle it. They've got some people that know what they're doing, so they're going to run them for us, and you'll see some things you probably haven't been able to see. And there they are, 15-inch refractor, 30 and 20-inch Dobbs. Sleeping accommodations. The club pays for 2 dormitories, 1 for men, 1 for women. 6 cabins, only 6, and there's a lottery for that, and those are pretty nice cabins. Limited number of RV hookups. They have RV hookups that only have electric, and then they have RV hookups that have electric and water. The problem, the ones that are water, they're out away from the encampment. The ones that are electric are close to the encampment. There's a Saturday night meal for the group if you want to attend that, and members are responsible for their own meals during normal time. Next slide. Acorn 2026. Registration is on now. That's going to be August 12th, 15th, 2026. So this is another really cool thing to go to. Next slide. Monthly reports, general outreach report. Patrick, you got anything real quick? I'll meet you halfway, man. Oh, no, I won't. You got to be on camera. I know. We're trying to get through it.
Okay, so just a few. I posted some earlier today. We got Whiskey Ranch Solar Party this Friday, but the weather's not looking good for that. Also have one up in Bridgeport. If I can get maybe one or two other scopes to help me there, that would be good. Then on June 25th, we're actually going to do a star party for the Benbrook Public Library. And then there's another Whiskey Ranch solar party on July 3rd. Next slide. And then on July 17th in Richland Hills, there's a BioBlitz stargazing star party, and they're also going to do a mothing at that time. Again, I'll put these on the e-group.
Thank you, Patrick. Tandy Hill, John, there you are.
Okay, our Tandy Hill Star Party is this coming Saturday. Right now the weather looks iffy, like it normally does. I put out an email, I want to make a correction. I put out an email saying that from Tandy Hills you can see 2 to 3 stars. I was wrong. I was informed tonight that you can see 10 stars out there. So I just wanted to set the record straight. So if you're looking for a new telescope, if you have a telescope that you need help with, anything like that, just come on out. We love helping people with scopes, and I want to thank the ones that came out in May. We had about 8 people, and we had 2 of our new members that were there, and about 20 to 25 members of the public out there. So come on out. That's this coming Saturday, the 20th, and if it doesn't rain, we should see a moon and Venus and maybe 10 stars.
Yeah, if the clouds clear. Young Astronomers Outreach, Cy, you got anything? Okay. And 1687 Foundation, Bob, got anything? Okay. This is another good one you need to make. I've been out there twice and I've had good times both.
So we will have an event in July. I don't know the date yet. I got an email from Sarah last week, I think on Tuesday actually, so we're trying to get that sorted out. It'll be kind of hopefully not too last minute, and we're going to have 4 in the fall. So I think 2 in September and 2 in October, so it'll be busy in the fall for us. Thanks.
Everyone at that facility has a great time when we come out there and hold a party. Okay. No, you're going too fast. Here she is. She's getting up here.
Palo Pinto, I want to thank everybody who came out this past weekend. We had 20 scopes from what I counted out there, and we ended up with probably 100 people who came through, maybe a little bit more. Everybody, it was actually well behaved. Everybody took care of the kids. It was very good. And not all of the people who come to the star parties at the state park are camping there. Some of them are actually traveling from the Metroplex or from Abilene because the park posts it as one of their events. So we do get people coming from the Metroplex just for the star party. We had a couple of people who were asking possibilities of membership. We had some who had questions about different telescopes. The next scheduled star party at Palo Pinto is going to be July the 11th. Yeah, July the 11th, and we'll get that posted also, okay?
Yeah. I was out there last time. I posted 2 pictures. I don't know if everybody saw those, but anyway, it was really a big show. Rising, okay, we're going through Fort Worth Rising Star Summer Special. Tom kind of talked about that, so I think we can jump past that. That's Saturday, June 20th. Put that on the calendar. Cross Plains Public Library, me? No, I got nothing. Cross Plains, yep, nope. Monthly announcement, we're at website and media. George, anything? I guess not. Oh, well, okay. Oh, wait a minute, Bob. Get him a mic. There you go.
The Noble Observatory website is noic.fortworthastro.com. It's up if you want to kind of poke around at it. We'll be having Zoom sessions on how to use it, and we plan to go live with the Noble in July. So just thought you guys would like to know.
Outstanding.
Next slide.
Okay, next slide.
Okay, so next month, it's not confirmed, but we have talked, and he said that he was available. So we're gonna see with this Dr. Penpraise about the structure of galaxies. So ought to be a really cool one there.
Okay, next slide. Okay, some of us meet at the social house after this gathering. Beer, appetizers, some munchies. It's a nice little bar restaurant. It's just like half to 3/4 mile from here toward town. It's very easy to get to. That's the address. If you're interested, I took a picture, entered it in my GPS, and it took me there the first time, no problem. Yes. We're going to be here probably for 2 weeks? 2 months. We're going to be here for 2 months. At that point in time, they'll give us options of where they're going to send us next. So, anyway, next slide. Thanks for attending.